The periodic table is one of the most important tools we have in science, and there's a lot of information packed in a very, very small space here. We're going to spend just a brief couple of minutes looking at some of that information, starting to unpack it, and how we actually use this tool to do a lot of the rest of the chemistry we're going to be doing for the rest of the year. So we've looked already how to write electron configurations from this. We've looked at some of the names and kind of how it's organized. But we're going to add on to that the idea of what it actually means to be periodic, the periodic table. The periodic table is called the periodic table because it has repeat properties every period. The periods are each row, and within each row, as we move in our second row, in our second period, from lithium to beryllium to boron, and in the third row, sodium to magnesium to aluminum, we see a lot of the same properties, how they combine with oxygen, how they melt, the melting points, the chemical reactivities, the other physical properties are very, very similar. So they're so similar, in fact, that we have names for all of the columns, since those all act alike. Here we have a list of all of those names, the important ones that we know of. The first column we call the alkali metals. So this first column right here, that is our alkali metals: lithium, sodium, potassium, rubidium. Alkaline earth metals are then the second column, the beryllium, magnesium, calcium column. Those all act very similar, so they're all called the same, in the same family. Transition metals, this entire D block, is lumped together because, as we've talked about with our electron configurations, really only the S and P electrons are participating in chemical reactions. So all of those D elements behave pretty much the same way. Same as down here in the F block, the lanthanoids and the actinoids. Those are all lumped together because they all behave very, very similarly. Once we go over into the P block, then we have some similarities, again, that show up very specific to what column it is in. Way over on the right, we have our noble gases, immediately preceded by the halogens, and then the chalcogens, where we have oxygen, sulfur, selenium. So they all, everything in that column behaves very, very similarly, and is called a family, or a group. So two names for that: groups or families. If we think about the periodic table, how it actually should be drawn, again, remember that that F block should be in between the S and the D. It's just moved down below because it fits nicer on our pieces of paper. So from this point forward, instead of talking about rows and columns, we will be talking about periods. Periods are the rows, so the first through the seventh period. And the groups, or again, families, are the vertical columns. So the halogen family, or the halogen group, might be here, and the sixth period would be there. Within the periodic table, we also have a few other divisions, a few very important divisions, most notably metals, nonmetals, and metalloids. If we take a look at the periodic table that we have in class, we have we do not have a stair-step line on this table as we do on a lot of tables that we've seen, and I strongly suggest that you actually write it in there. It starts up here at the top of the P block, top left in the P block, and from there we go down, and then every element, we just stair-step our way all the way down, and that separates the metals on the left from the non-metals on the right. You can see that about 4/5 of our elements are all metals, and non-metals comprise just a very, very small portion. Also, you notice on this table, most of those metals are blue, which indicate they are solid at room temperature, and a lot of our non-metals are red. We have a few other properties that we want to add in as well. So thinking again about just the S and the P, the metals have only 3 or fewer outer electrons, which we will call valence electrons in a little bit. To gain their stable configuration, as it says up here, the electron configuration of a noble gas of S2P6. It doesn't matter which energy level, but S2P6 is the most stable electron configuration. And so to do that, we need to either gain enough electrons, an atom needs to gain enough electrons to become 8, or it needs to lose all of its outer electrons and thereby reveal a full energy level 1 level below. So to do that, a metal will be much more likely to lose those electrons, and since electrons are negative, they are then going to be forming positive ions. And an ion, right now we can think of an ion just as a charged atom. We will refine that definition a little bit later in the course, but right now it's an atom that has either gained or lost some electrons and therefore has a charge to it. So what do metals look like? Well, think about the metals that you see on a daily basis. Metals are almost always shiny, or another way of saying that is they have luster. They're very, very conductive, conduct heat and electricity very, very well. They are malleable and ductile. And most are solids. Most are solid at RT, stands for room temperature. Now, if we think about the nonmetals on the right side of the table, those are going to have almost all opposite properties. They're going to have 5 or more outer electrons. They're going to want to gain electrons to form negative ions. And the properties of nonmetals are, again, pretty much reversed. They're not shiny, they are very dull, or another word for that is lackluster. They do not conduct, therefore they are insulators. A lot of them, almost all of them, are very, very brittle. And you know that if you're writing with a mechanical pencil, you extend the graphite a little bit too far, it snaps right off. It's a very brittle compound, carbon is. And many are gas at room temperature, which we see by them being red on the periodic table. Metalloids are everything touching that stair-step line except for aluminum. They have the properties of both metals and nonmetals. And it leads to some very, very interesting properties in a lot of compounds that become very, very useful for us. Most notably silicon, and we have an entire electronics industry based around silicon. So computer chips are very important. They are based on semiconductors, which are metalloids. Transistors, other electronic devices. Without metalloids, without these semiconductors, hardly any of our electronics would be usable or would be in existence. So again, everything except for aluminum touching that stair-step line that we drew earlier is a metalloid. Aluminum we know is a metal. A lot of us have, we have personal experience with aluminum foil, and aluminum fits the metal definition very, very well. But everything else touching that line, boron, silicon, germanium, arsenic, antimony, as we go down, is a metalloid. So the metalloids, the ones that are normally considered metalloids, are B, Si, Ge, As, Sb, Te, Po, and At. You can see those are everything touching that line except for aluminum. There's a lot of various trends that behave what's called periodically with a very predictable pattern as we move around that table. One we're going to look at right now is atomic radius. The rest we're going to leave for later. But atomic radius fits, it's quite intuitive if we think about how big an atom is and sort of how large that electron cloud is around it. The radius, remember the radius of anything, is the distance from the center to the edge. And so in this case, in the center we have the nucleus. So the atomic radius is the distance from the nucleus to the very outermost electron. The units we use for this are picometers, 10 to the negative 12 meters, and most atoms are in the neighborhood of anywhere from 40 to just a couple hundred picometers in diameter. Very, very, very small. So if you think about what determines how big that cloud is, how far the outer electron is from the nucleus, there's two main things that impact that. Number one is how far, what the outermost energy level is that's populated. As we move down the periodic table, from top to bottom, we are adding energy levels. Adding energy levels of electrons, thinking about that principal quantum number, which means every energy level, as we move down, we will increase the size of that atom. So looking at the table, lithium will be smaller than sodium. Sodium will be larger, then potassium will be even larger, rubidium will be even larger. Moving down the alkali metals, the alkali group, every time we add an energy level, it gets bigger and bigger. The trend from left to right, we're still adding electrons, but it actually is a little bit not intuitive because it actually decreases as we move from left to right. Even though we're adding electrons, and the reason why that actually makes sense is in the same energy level, so we're not adding a greater energy level, but we have more protons in the nucleus and more electrons in the cloud. And positive and negative charges attract to each other, which means that added protons pull on added electrons. A greater pull from the nucleus means there will be a greater pull, or a smaller final result. So we get, the atoms get larger as we move to the right, and they get smaller as we move down, which means that the absolute, again, there we are, the absolute largest atom that we have is francium, and the smallest is helium. There's 4 examples that we had there on the previous slide of which element is larger. And if we look, it says here cesium or francium. So those are down here on the lower left. And francium is going to be the larger one. There's an extra energy level there. Number 2, it says nitrogen or oxygen. Those are up here in the second period in the P block. We get smaller, the atoms get smaller as we go to the right. So nitrogen is the larger atom there. Vanadium, where are these here? Vanadium or novium, those are in the D block here. Novium is going to have an extra energy level, so that one's going to be larger. And either ruthenium or cobalt, these are actually on a diagonal, so we have both trends coming into play, but they are working in tandem. Ruthenium is a period lower, which means that it is larger, and it's also one fewer proton-electron attraction, which means it is a larger atom as well. Now with all this information, we can figure out our periodic table puzzle. Taking a look here, this is really just using the information in that packet and from our electron configurations to determine kind of where each of these pieces are. The groupings that we have over here on the left are families. So I know that J, K, and Q will all be in the same period, or in the same column, excuse me. Same with W and VG, Y, B, R, etc., etc. I need to use my clues up here to place those. So it says here V is an inert gas, which means that I know that that period, those 4 elements will all be in the far column here. So in this one, I'm going to have W and V and G. I need to look for some other clue to place those. Here we have one tells me G has only 2 protons. Well, I know that has to be helium then. And we can kind of keep going from there. The, let's see, W, N, or V.